Hey, welcome back. Today's lesson's on exponential growth and decay. Now, all exponential functions, we're going to look at a lot of them today. They all come in the same form. We have two numbers and one of them is being raised to an exponent. So if the variable is not in the exponents, then it is not an exponential function. That x has to be an exponent. Hence, exponential function. Okay, so the first number that we have, we call the initial value, and that can't be 0. That's our first condition. And the number that's being raised to a power, that's called the growth factor or the decay factor. It's what you multiply by. So as x increases, you can see that we're going to multiply by b. If x equals 1, we have 1b. If x equals 2, we're going to have b times b. It's going to be a times b squared. So that's a times b times b. If x equals 3, it's a times b times b times b. So you can see that you're just multiplying by b each time. And that's why it's called the growth factor. Or if it's getting smaller, we call it a decay factor. Now, b has to be not equal to 1. That's the only, it has to be positive, it has to be not equal to 1. Those are the two requirements. If b equals 1, then you're just multiplying by 1 and your function's pretty boring. All right, so if it's greater than 1, we call it growth. And if it's less than 1, but it has to be positive, it has to be greater than 0, then we call it decay. All right, so let's look at the differences between exponential functions and linear functions. We know with linear functions, here's the line y equals 2x. Notice how, for every increment of x that you increase, you add 2. So this is adding 2, adding 2, adding 2. And that creates a linear function. All right, this is linear. Because you add the same amount every time, it creates a line. But if you start multiplying, this is 2 to the x. So when x equals 0, remember anything to the 0 power is 1. So you can say the 0, 1. And a lot of exponential functions go through 0, 1 because they're in this form. And when you raise it to the x power, if x is 0, you get 1. I mean, wow. Okay. But let's look at the function if this value right here, the growth factor, is not equal to a positive number greater than 1. What if it's a decimal or a fraction? Notice what happens to the curve. So this here is a growth function, growth. However, when that growth factor decay is less than 1, we get a decay function. And notice the decay function comes down and it levels out eventually. And we'll talk more about the graph later. So let's go through these different examples and see if we can figure out what the a value is. Let's look, f of x. I'm going to write it right here. This is what we're looking at. So it's ab to the x power. So let's see if we can figure out what the a value is, what the b factor, or what the b value is, and whether it's growth or decay. Okay, so the first example we have, we graphed it up here. A, is it exponential first? Yes, it is. That's definitely exponential. The a value, what number is in front there that we're not writing? A is equal to 1. And that one, this is really this. 1 times 2 to the x. And so the growth factor would be 2. And it's growth, not decay, because it's greater than 1. Easy enough? How about the next one? We have x to the negative 2 power. Well, for exponential functions, x has to be positive. So this is not exponential. So this stuff doesn't make sense. Next example, we have 4 times 0.1 to the negative x. Let me rewrite that over here. So we have 4 times 0.1 to the negative x. Well, I'm going to use our exponent rules, which I know you guys all love because you just passed a mastery check, right? This is 4 times 0.01. Instead of negative x, I'm going to rewrite it like this. I'm going to take that negative 1 out and make that x positive. So all exponential functions have to be written so that the x is positive. Now, if I take, this is really 1/10, and I raise it to the negative 1 power, I get 10. So I've rewritten that. Just put this in your calculator, and you'll get 10. So this is 4 times 10 to the x when I rewrite it. So this is exponential, yes. It's just written in a different way. A equals 4, and b is going to equal 10 here. And because b is greater than 1, it's growth. All right, how about the next one? 2. All right, what do we got? 2. That's the value of a. B equals 0.5. That means it's a decay function. Yes, this is in the proper form. All right, how about the next one? We have x in front. X is the value of a. That's the variable that's changing. So this is not exponential. Remember, the exponent has to be the variable. And right here we have a 5. So no, that's not one. All right, why don't you try the last two by yourself? Go, pause the video. Okay, back we are. Here we go, the first example here. Is it exponential? Yes, it is, because what do we get here? A is 10, and we have to work it out. So this is where the work is for that. I came back. So that's 6 to the negative x. Well, negative x, I rewrote it. Okay, it's 6 to the negative 1, and that's raised to the x. And then 6 to the negative 1 is 1/6. So this is exponential, and a is 10, and b is 1/6. It's a decay function. For the last example, you notice that b is negative and b must be positive, so that is not exponential. All right, so now we're going to look at creating equations to match the scenario. So we're just going to make sure that our equations are in the form of ab to the x. We have an initial value and then a growth factor. So the first example, a local college has increased its number of graduates by a factor of 1.045. All right, so that tells you right there, that's the growth factor. So that's going to be what b is equal to. Right there. All right. In 1997, 924 students graduated. So this is the initial value. So let's write it. So f of x, we're going to use our function notation, equals, we start with our initial value, multiply it by our growth factor, and raise it to the x power. And we're done. There's the equation there. How many students will graduate in the year 2005? Well, to get that answer, we're just going to plug in. Well, we're not plugging in 2005 because this is every year since 1997. So how many years has that been? That's been what? 1, 2, 3, and then 8 total. Okay, so we're going to plug in. X is going to equal 8 here. And we're going to plug that into our equation. So f of 8 is going to equal 924 times 1.045 raised to the 8th power. When I work that out, I get 1,314. So that is our answer to the last part. F of 8 equals 1,314 students, approximately. And of course, because there's a decimal, you can't have a 0.02, so we're going to round that. All right, next one. Sully's Dance School currently has 520 members. That is going to be our initial value right there. So that's what A is. Every day, 1/4 of them quit. So I'm going to write, what do we got here? So f of x is going to equal 520. And then every day, 1/4 of them quit. So we have to be careful here. I don't want 1/4 of 520. I want to see how many are left. That's what this function is asking, like how many are left. So if you take a fourth away, that leaves 3/4. Sometimes we got to be tricky there. We got to be careful, right? If 1/4 quit, then 3/4 are left. And we're going to raise that to the x power. So how many students will there be at the end of 1 week? And because this is in days, that means I'm going to plug in. We want to find here. Let's change color. All right, so f of 7 is going to equal our initial value, 520, times 3/4 to the 7th power. That's going to be our exponential function. You can see as we work that out, make sure that you use parentheses in your calculator. And all of that will equal 69.4 students. So we'll just leave it at 69 students. We're going to round that. Okay, on to the last one on this page. Now this one's a little bit different because they don't really just come out and tell you A and B. What they tell you is that in 4 days, the population of fruit flies, which is currently at 150, it increases to 400. So looking at our function, let's just write our function out. So f of x equals ab to the x. What do we know here? We know that in 4 days, so if I plug a 4 in, so f of 4 will equal 400. So let's write that down. 400 will equal, if I plug a 4 in. Now, I also know that 150 is the initial value. So really, we're just stuck with finding for the value of b. We don't know what the value of b is. So if I divide both sides by 150, let's do that in this equation. And then we get, what do we get here? That reduces to 8/3. Is that right? I do that right? So 8/3 is going to equal, they're going to cancel b to the 4th. So how do we solve that equation? You can do it either one of two ways. You can raise it to the fourth power or take a fourth root. I'm just going to raise that to the fourth power. So b to the fourth to the 1/4 power. And that'll get those exponents to equal 1 when we multiply, right? So b to the first, kind of ran out of room here, is going to equal 8/3 to the 1/4 power. Got to work that out. And you can see down here, we got 400 divided by 150. Put it into a fraction, and then we raise that to the 1/4 power. I get 1.27. I'm going to call it 1.28. We're going to round a little bit. So b equals 1. Ooh, I want to be drawing right now. What's going on? So 1.28 is the value of b. Now, how many fruit flies will there be at the end of 1 week? Well, first let's write our function out, because we never really did that. Our function is going to be f of x is going to equal, we have the initial value of 150, which they told us, and we figured out that b was 1.28. That's raised to the x power. So what do you get when you plug what do we want to plug in? 1 week? And we're talking about days. So that is 7 days. So we want to find f of 7 here. So f of 7 is going to equal 150 times 1.28 to the 7th power. Let's work that out. So when I plug it into the calculator, you can see how I did that over here. I get f of 7. I am running out of room here, aren't I? F of 7 equals, about 844 fruit flies. Wow. Those fruit flies, they're crazy around here. They're crazy. All right, next question. One of the most useful applications of exponential equations are doubling and half-life formulas. So go ahead and pause the video and write these down. We have the doubling formula here on the left, doubling, and the half-life. And you can tell the difference. Ooh, I wrote half-half. What up with that? This is half-life. And you can tell the difference based on the growth or decay factor. So where there's a 2, obviously that's the doubling. And if it's a half, it's a half-life. Now, if you notice, the form changed a little bit because our exponent became t over x. Well, x here is the doubling. It's the time it takes to double. So I'm going to write time to double. Or we call that the half-life. If we're doing a half-life problem, it's the time it takes something to decay to half of whatever you started with. Now let's see how it works with the first example here. There are 500 grams of radioactive material. Its half-life is 5,700 years. This is how they figure out how old stuff is, by the way. You should know that. Take chemistry. You taking chemistry? Anyways, so let's write this. F of t, we're going to change it up. So our time is t here. It's going to equal, we're starting with 500 grams. So that's our initial value. And we're doing a half-life problem. And the half-life is 5,700 years. So that is what goes on the bottom. So we're going to write that, 5,700. And they want to know how many grams will there be in 20,000 years. So we're going to find f of 20,000. That's going to equal 500, 1/2 to the 20,000 over 5,700. And when I plug these in, just to make sure I always put it in the right place, I ask myself, that's about 4 half-lives, right? 20,000, because a half-life is about 5,000 years. So when I write my fraction, make sure that you're putting the bigger number on top so that you get about 4. Let's put that in the calculator. So when I plug that in, I get 43.92. So f of 20,000 is going to equal 43.9. I'm going to round that up. 93 years. No, not years. Grams. Right, because we're figuring out how many grams are going to be left. Goodness gracious. You got to answer the question they're giving you. How many grams will there be in 20,000 years? All right, why don't you try the next one? Pause the video, do the next one by yourself. Go. Okay, so did you figure this out? We have years and months in this problem, and they're telling you it doubles every 6 months. So this problem has to be in months. So 5 years is 60 months. So we're going to use 60 here. You got to put 60 over 6, and then you figure it out. You get 500 112,000 rodents. Whew, Mr. Bean's house. It is in the forest. In the forest. All right, so now let's look at what these look like on a graph. All right, we have our two different types, growth and decay. If b is greater than 1, that's a growth function, then the graph will grow away from the asymptote as you move left and right. Okay, we'll see what that means here in a second. If b is less than 1, or if it's a decay function, it'll grow towards the asymptote. And we put that into quotes because growing towards something means it's approaching it. An asymptote, okay, this is an imaginary line that the graph approaches more and more closely, but it never really crosses it. So let's look at these functions here, see if we can figure out whether they're growth or decay. And sometimes it's opposite of what you might think. Like with the first, well, let's go to the first one here. Now, do you see how the numbers, we start and there's slow movement. The numbers don't really move a lot. But then as x increases, these things start to shoot down. They're going crazy. They're going down quickly. Okay, this one here is a growth function. Now, a lot of students think it's decay because it's going down, but it's not. This is actually growth. It's growing away. Think of it like something growing into the ground. The roots are growing down. It's going away from the x-axis. This x-axis right here, y equals 0, that is the asymptote. So we're going to actually draw that for each one of ours. We're drawing the asymptote. This is y equals 0. And so this function approaches y equals 0 as you go left, but as you go right, it grows straight down. All right, let's look at the next example. We have another asymptote here at y equals 0 again. Now, is this growing away from it, or is it growing towards it? Well, this is growing towards. See how it's getting closer and closer? The values are changing more slowly, more slowly, more slowly, more slowly. This is a decay function. All right, so that's the difference between the two. Pause the video, do the next two by yourself. Go. Pause the video. All right, so what did you get? Do you notice how this function here is getting closer and closer to the line, but it's not going to cross? It's not growing away from it. That means this is a decay function. And make sure you label that asymptote. This is y equals 2. It's the line y equals 2 straight across. That is the asymptote. For the last one, the asymptote's at y equals -2. We can see that, but notice how the function's going away from it. That would be a growth function. All right, so now we know what they're supposed to look like. We can actually put them on a graph. So graph f of x equals 3 times 2 to the x. Here's how I graph the exponential functions. What I do is I try to make that exponent a 0, and then we're going to build a table of values. And if we know what it looks like, and we have a couple points, we can draw the function. It doesn't take too much work here. So I know that if x equals 0, my exponent here will be a 0. So I'll get 3 times 2 to the 0 power. All right, anything to the 0 power is 1. So that's just 3 times 1. That equals 3. So I start this graph at 0, 3. Okay? Now, the next thing I do is I use values around 0. So I'll go up to 1. It looks like we're just building a table off of guessing and checking. And really, that's kind of what we're doing. So I plug a 1 in. So what is 3 times 2 to the first power? Well, that's 3 times 2. 3 times 2 is 6. Okay, so at 1, we're at 6. So 1, 2, 3, 4, 5, 6. We're up here. Now, I might even go backwards. I want to know what this point is, so I'm going to plug in a -1. Okay, when I plug in a -1, I get 3 times 2 to the -1 power. Let me do that over here. 3 times 2 to the -1 power. You can do it in your calculator if you want to, but that's the same as 3. Remember a negative exponent? 1 over 2 to the positive. That's going to equal 3/2, or 1.5. So for -1, I get 1.5. That's right about here. All right, I have 3 points. 3 points is enough. I'm going to draw the line so it looks nice, and it's got to be curvy here. What are we doing? Now, which points can you pick for your table? You really can pick any points for your table, but what I want to focus on is making that exponent a 0 first, and then I pick points around that. The domain of this, well, let's talk about domain. Where does this go? This is going to go up forever, and is it going to ever, can we plug in any x value here? Can we plug a 10 in? Yes, we can. It'll be a super high number, but we can plug a 10 in. We can plug 100 in. Can we plug negative numbers in? Yes. Notice how all of the x values get used here. So the domain here, all real numbers. What about the range? Well, we have an asymptote at y equals 0. So we need to plot that on our graph. Let's do that. Y equals 0 is our asymptote. And so our range is going to be, it always gets closer to 0, but it never gets there. It never quite gets there. It's always closer and closer as you're moving left. So the range here, f of x. I was going to write y there for a second. It's the same, f of x. So f of x has to be greater than 0. All right, and this is a growth function because it's going up.
I'm interrupting your regularly scheduled video at this point because at this point in the algebras video, they use a graphing calculator in order to help out with some of these questions. And because you guys don't have a graphing calculator, I'm going to show you how to use Desmos for the same thing. So let's take a look first at the question and then how a graph can help you out. So number 2, graph f of x equals -6 times 1/3 to the power of x. So same as you did in the previous question, you want to create a table of values that is x f of x. So there's some space here for you, hopefully to create a little bit straighter line than I did. X f of x is my table of values. And I'm going to start out with making the exponent equal to 0 because I know that makes life easy for me. 1/3 to the power of 0, anything to the power of 0 is 1, and then 1 times -6 is going to be -6. So that's an easy point to put on my graph. And then I'm going to build the rest of my graph around this x value of 0. So I might try plugging in, let's say, an x value of 1. So 1/3 to the power of 1 is 1/3, and -6 times 1/3, -6/3 is going to be -2. If you need to actually type that into your calculator to reassure yourself, -6 times 1/3 is in fact -2. You can do that, no worries. Let's go in the other direction from 0 then and see what happens when I type in a -1. So remember that a -1 as a power is going to flip this fraction. It's going to get me the reciprocal. So 1/3 is going to flip to get me a 3, and 3 times -6 is -18. Well, that's going to be way off my graph down here, so I'm probably not even going to end up plotting that point. So let's pick at least one more point that will be useful to me. So if I plug in an x value of 2, -6 times 1/3, well, let's see, that's going to be 1/3 squared is 1/9, so -6 times 1/9 is -6/9, which reduces to -2/3, or 0.666666. So this is going to be -2/3 on my graph. And again, you can double check that. -6 times 1/3, whoops, 1/3 squared tells me is -2/3. So let's see if I can put these on my graph. I'm going to start at 0, -6 gets me right down here. Then 1, -2, sweet. -1, -18 is super far down here. So again, it's going to be not even on our graph, but hopefully that gets you an idea of where our graph is going. And then 2/3 is about there. And I can kind of sketch in from there what kind of thing is happening. Oops, missed that point. I want to actually go through those points on my graph, otherwise it wasn't much use to make them. So again, coming closely to my asymptote, which is y equals 0. It's coming along here on the y-axis. And I use my table of values to plot a few points along the way. So growth or decay, well, we know that if we're getting closer and closer, sorry, I've got the arrow on this end, make sure you have an arrow on both ends of your graph. If we're getting closer and closer and closer to our asymptote of y equals 0, that is going to be a decay. The other way that we know that is because this number here is less than 1, 1/3 less than 1, so we're looking at a k function. Domain is going to be all real numbers because there is no value I could not plug in for x, so I've got this double bar r to signify all real numbers. And looking for my range, which is my y values or my f of x values. Remember that f of x is just another name in this case for y. I have f of x, my y values are all going to be down here under y equals 0. So this is going to be f of x less than 0. So how does Desmos help us out with this? Well, let's pull it up and actually just go ahead and type in this function. So it's going to be negative 6 times 1/3 to the power of x. So here's my Desmos, and I type in here y equals. You can type it in straight off your keyboard, or if you want, you can click the show keypad and click on here y equals. All those values are available to you. So I had negative 6, so I'm going to go negative 6 or subtract 6, parentheses. Now to get a fraction, you can use the slash bar on your keyboard, or you can also go to, give me a second, functions, no, how do I get fractions again? Alright, I just used the division sign on here, so if I want 1/3 is going to be, whoops, I need to be inside 1 divided by 3, it will automatically turn itself into a fraction, close that parentheses, or just arrow over to get outside the parentheses, and then I'm going to hit to the power of is this one right here, or it's the caret key, the shift 6 key on your keyboard, and then I'm going to put in here is my x. Collapse the keyboard, and there it is. I've got my function showing. Here's that 0, negative 6 I was talking about. I should also be able to pick up on the 1, negative 2 would be right here. You click on it, you can see different values along your function. You can also see that we're getting closer and closer and closer and closer to 0. It says we actually get to 0, but it's just so close, it's such a small number that it doesn't know the difference. But there it is, getting closer and closer and closer to 0. Now, if I wanted Desmos's help in making that table of values, I would click here on those little edit list, and then there's this convert to table. So actually, before I actually do that, I'm going to go back. So it's this edit button. Whoop. Somehow I lost the x. Come back. X to the power of x. Convert that, and I'm going to click on this convert to table. And there it has all the different values from negative 2 to 2. So again, here's my negative 1, 18, my 0, negative 6, my 1, negative 2. This is 2, 2/3. If I wanted another one, I can just type in below that, or I can go the other direction, negative 3. Doesn't have to be in order. I can type or change any of these, and it will give me the values that I'm looking for. And they appear on my graph now as actual points. So that will help you out when you want to graph a function. Now, when you're using Desmos with your own work, you do need to still write down this table of values and plot those points on your graph, but you can use Desmos to help you generate the table. You can't just put the line on the graph any which way. You do need to have these points on there, the 0, negative 6, the 1, negative 2, the 2, negative 2/3, so that you can actually see what points your graph goes through. Don't just draw a random line, but you can use Desmos to kind of help you out with that. All right, let's take a look at number 3. Graph f of x equals negative 2 times 3/2 x plus 4 plus 3. This is about as difficult as it's going to get. So again, start out with our table of values of f of x, and remember f of x is just another name for y. So here's my x, here's my f of x. And this time I'm not going to start out with x equals 0, because if I plug in x equals 0, I've got 0 plus 4. This is going to be actually a lot more mental math work than I'm wanting. So what I am going to do is see what value would make this exponent equal to 0, so I can get this whole thing equal to 0, because something to the power of 0 is 1, and that would just make my life a whole lot easier. So in this case, what plus 4 equals 0? Well, that would be negative 4 plus 4 equals 0. So that makes this whole exponent 0, and this 3/2 to the 0 is 1. Negative 2 times 1 is negative 2 plus 3 is just 1. Now you could type all that into your calculator if you like. Negative 2 times 3/2 to the power of 0 plus 3 is 1. Or you can even make this negative 4 plus 4 if you like, just to reassure yourself that I've got the point negative 4, 1. Then I'm going to pick some points around here, so I'm going to pick maybe negative 3, because negative 3 plus 4 is going to be 1. So I've got negative 2 times 3/2 is going to be then negative 3 plus 3 is going to be 0. Again, you can go ahead and do as much of this on your calculator as you like. Just be careful when you're typing things in. Okay, so I did on my calculator a few other values. This one was plugging in x equals negative 2, and I've got negative 3/2, which is negative 1.5. I'm going to put that on the graph, and then I've got, this would be, if I plugged in a -1, I end up with -15/4, which is -3.75. So let's see if I can put those points on the graph and see where we go. So -4, 1, -3, 0, -2, -1.5, -1, -3.75. And one aspect of this graph, you can kind of see what the shape is doing, but you can see that I don't have an asymptote at y equals 0 anymore. This +3, as we learned from our unit on transformations, is going to move my graph up 3. So instead of having an asymptote at y equals 0, I've actually got an asymptote at 1, 2, 3. Here we go. So here's my asymptote at y equals 3. And I've got this, as you can see going on, it's going to get closer and closer to 3 and come down on the other side in the other direction. So again, let's check how we could use Desmos to help us out with this. This is a bit more a complicated function to type in, but we can still do it. So -2, 3/2, x plus 4 plus 3. Here we go. I'm going to clear out one that was already in here, and y equals -2, whoops, y equals -2, 3/2 to the power of x plus 4, nope, it's not gonna let me, parentheses, x plus 4 plus 3. Okay, so here are the points that we would expect. We've got our -4, 1. Actually, let's just convert this to table right away. And I'm gonna have to type in some of those numbers. So instead of -2, I'm gonna go -4, -3, -2, -1. I don't really care about the rest of them down there. So we've got here -4, 1. Here's my -3, 0. Here's my -2, -1.5. Here's my -1, -3.75. And if I wanted to go lower, I could. So again, you could use Desmos to help you create this table of values, but you do need to include it on your paper. Here's my table of values that I used to figure this out. Now, growth or decay. So in this case, it is going to be growth because we are moving away from my asymptote, or this number is greater than 1. So 3/2 is greater than 1, and in this case, we had 1/3 being less than 1. So this is a growth function. Again, we can plug in just about any x value you can think of. This is going to be domain of all real numbers. And my range, looking again at the graph, what I've got going on is we're going closer and closer and closer to 3 on my y values. So I've got f of x is going to be less than 3. So it's below 3 on my graph. And that would be it for this second one. So here's your little bit of a summary of your steps for graphing exponential functions. So build a table for x, f of x, and start with a value of x that creates an exponent equal to 0. So a lot of times that's going to be plugging in 0 for x, but not always. In this case, we plugged in -4 because we had -4 plus 4 equals 0. So we want to get an exponent equal to 0. Then we're going to fill in the table with values around this x value. So in this case, it was values around -4. We had -3, -2. Now we want, in this case, it was values around 0. We went in both directions and see where we got. And then last but not least, you need to always label the asymptote. So in this case, it was y equals 0 because it hadn't shifted at all. In the second case, it was y equals 3 because it had shifted up 3. So that's it for this lesson. Good luck on your homework and your mastery. Cheers.